Welcome to this session. This session is solve a problem involving two surfaces or a surface and the other family of surfaces given by the equation specified by this and then this other question. So the main work is to show that this surface and family of surface defined by this equation are always perpendicular. And then the point of intersection is 1 minus 1 and then 2. Now what you have to do is to define the functions defining the first equation of the surface, and then get the partial derivatives, which are the direction ratios, and then find their values at the specified point 1 minus 1, 2, and then also find the partial derivatives of this other family of surfaces, which define the direction ratios, and replace the values with 1 minus 2, 1 minus 1, 2 for x, y, and z respectively, and then show that the dot product of those two direction ratios in the first case and the second case is 0. That is what confirms that those two surfaces are perpendicular. So this is what I mean. So case 1, solution. So we have x squared minus 2yz plus y cubed is given by 4. So just take this 4 to the left so that we have x squared minus 2yz and then plus y cubed minus 4 equals to 0. Now this equation, call it f. So let small f of x, y, z be defined as x squared minus 2yz plus y cubed minus 4. And so let's get the partial derivative of this function with respect to x, y, and z, which define the direction ratios for that given surface. So partial f, partial x, for this one we get 2x, and which means partial f, partial x at the specified point, which is 1 minus 1, 2, 2 times 1, which will give us 2. And then partial f, partial y, this will give us minus 2z plus 3y squared, which means partial f, partial y at 1 minus 2, 2, 1 minus 1, 2 is minus 2 times 2 plus 3 minus 1 squared. So minus 4 plus 3 is minus 1. And then partial f, partial z, this function will give us minus 2y, which means partial f, partial z, the specified point 1 minus 1, 2 would be minus 2 times minus 1, which is 2. Now, the partial derivatives, this first partial derivative with respect to x, with respect to y, with respect to z, are the ones that defines direction ratios to the normal of the tangent plane of the first surface. So we say the direction ratios to the normal of the tangent plane to the surface f of x, y, z equals to 0 are usually given by partial f, partial x, partial f, partial y, partial f, partial z, which is the same thing as 2x, and then minus 2z plus 3y squared, and then we have minus 2y, and then so direction ratios at the point 1 minus 1, 2 are, we got the answers to be 2 minus 1 and then 2. We do the same thing to the second family of surfaces. So we had equation x squared plus 1 equals to 2 minus 4a y squared plus a z squared. So take all these terms to the left. So we'll have x squared plus 1 minus 2 4a y squared minus a z squared equals to 0. Now what we get on the left hand side, this one we call it capital F of x, y, z. So this family of surfaces defined by this equation is given by capital F of x, y, z equals to x squared plus 1 minus two minus 4a y squared minus a z squared equals to 0. So partial f, partial x, for this one we get, remember this plus sign, 2x, which means partial capital F, this capital, partial x to the point 1 minus 1, 2 is 2 times 1, which is 2. Partial capital F, partial y is minus 2, 2 minus 4a y, which means partial capital F, partial y at 1 minus 1, 2 is minus 2 into 2 minus 4a times minus 1. Here give us 2 into 2 minus 4a, which is 4 minus 8a. And then partial capital F partial z will be minus a minus 2az, which means the value of partial F partial z at 1 minus 1, 2 is minus 2a times 2, which is minus 4a. So the direction ratios of this family of surfaces is given by direction ratios of the ratios to the normal of the tangent plane to this family of surfaces f, y, x, y, z equals to 0 are 2x minus 4 plus 8ay, and then minus 2az, and then at the specified point, direction ratios at 1, minus 1, 2 are obtained 2, 4 minus 8a, and then minus 4a. So if we denote the direction ratios for the surface x, y, z equals to 0 by L1, M1, N1, and those for f, x, y, z equals to 0 be L2, M2, N2, then L1, L2 plus M1, M2 plus N1, N2 will give us 2 by 2 plus minus 1 times 4 minus 8a plus 2 into minus 4a, which is 4 minus 4 plus 8a minus 8a, and this gives 0. Now, whenever the sum of products of the corresponding direction ratios is 0, then that's a confirmation that the two are perpendicular. So hence, the given surfaces are perpendicular at the point 1, minus 1, 2. So that's how we do that problem. Thank you.